Hello everyone, today we're going to be finishing the gas notes and I'm going to be spreading this out over 3 separate videos that would have basically covered the double period that we would have at class today. I'm really sorry that I'm not there today, but we're going to do the best we can with what we have. So the first thing that we're going to look at is we're going to find the molar mass of a gas. Now remember, yesterday we were talking about the density formula in terms of gases. So if we look at your notes, it says the previous equation to find the density of a gas can be rearranged to find the molar mass of a substance. So really all we did here was take density equals pressure times molar mass divided by the gas constant and the temperature in Kelvin, and we just switched it around so we isolated molar mass by itself. And then we have equals density, your appropriate gas constant, temperature in Kelvin, divided by pressure. So if we look at this first example here, it says calculate the molar mass of a gas if 2.5 grams occupies 0.0875 liters, 685 torr, and 35 degrees Celsius. Lovely. So what I'm going to do is start out by rewriting my formula here. So the molar mass is equal to density times gas constant times temperature all over pressure. Now, one thing that I want to note here is that if I take the density formula right here, another way that I can represent this is by saying we know density is grams over liters, and those two things are given to me here. So if I didn't want to just pull out the grams and the liters and just find density automatically, what I could do is I could take really the density and have grams on the top times the gas constant times temperature and divide it by the volume times pressure. And that's the way that I'm going to demonstrate this one. So again, instead of solving for density, I'm going to have 2.50 grams. The R that I'm going to use here is the R that's associated with torr, which of course is on your reference table. So that is 62.36. And I'm going to multiply that times my temperature, which is 35 degrees Celsius, which we'd be switching into Kelvin, and then I'd ask you, and there'd be dead silence, and then somebody would answer, and that'd be 308 Kelvin. And we're going to divide that by the volume, which is given to us in liters, which is nice. So that's 0.875 liters. And then multiply that finally times the pressure, which is given to us yet again in torr, which is 685 torr. Okay, lovely, torr. I'll label that one. Why not? So if I work this out, I'm going to get 80.1 grams per mole, which is what we know as the gram formula mass. Now, if you're wondering about units here, just really quickly, we start off with grams, and then we take this gas constant right here, and we know the gas constant for torr is liters times torr, T-O-R-R, all over moles per Kelvin. And then we're multiplying this times Kelvin, and that is all over liters times torr. So if we got real fancy, we could say that torr cancels torr, Kelvin cancels Kelvin, torr cancels torr. Oh, there it is. Liters cancel liters, and we're left with grams per mole, which is what we want, and which is down here. So 80.1 grams per mole is our answer to 3 significant figures. All right, let's look at another example. Calculate the molar mass of a vapor that has a density of 7.135 grams per liter at 12 degrees Celsius and 743 torr. Looks like I was really in love with torr when I was making these. So I'm going to write out my formula again to calculate molar mass. So molar mass is equal to density RT over P. So for this one, they give us a density here. They tell us that the density is 7.135 grams per liter. So I'm just going to substitute that in, 7.135. And I have my R, because I'm dealing with torr, which is 62.36. And then a temperature is 12 degrees Celsius, so we convert that into Kelvin. So that's 285. And then we're going to divide that by our given pressure, which is 743 torr. So again, in this one, we're given the density, we have our gas constant, we have our temperature, we have our pressure. So when we solve this to three significant figures, it'll be 171 grams per mole, which we know is the gram formula mass. All right, now let's talk about volumes of gases in chemical reactions. Gases are important to understand due to the frequency of use in chemical equations. Often the volumes of gases consumed or produced are calculated in chemical reactions. Remember, and this is quite important, 1 mole of any gas is equal to 22.4 liters. So when we do this, we're going to need information concerning pressure, temperature, volume, and a balanced equation, depending on the situation and the information that they're giving us. So let's look at an example here. At STP, what volume of oxygen is required for the complete combustion, so we're looking at a combustion reaction here, of 10 liters of methane. So the first thing that we need to do is write out our balanced equation. So it's a combustion reaction, so I have a hydrocarbon. So it's CH4 plus oxygen gives me carbon dioxide and water. And then I need to go back and balance this. So 1 carbon, 4 hydrogens. I need to put a 2 in front of here. 2 times 2 is 4. That's 2 oxygens plus the 2 oxygens over here, which is 4. So I need a 2 in front of here. So first thing is always going to be writing your reaction correctly and then balancing it. Now, in a volume-to-volume situation, as in this example, recall Avogadro's law, which states the following. Equal volumes of gases at the same temperature and pressure contain equal number of moles of gas. This means that the volume of gases measured at the same temperature and pressure are in the same ratio as the coefficients in the balanced chemical equation. What does that mean? Well, the translation of that is basically that we're at STP. We're at the same temperature, we're at the same pressure. We don't have to worry about anything weird, so we don't need to use the ideal gas law. We don't need to use PV equals nRT. Instead, all we really need to do is just a liters to liters stoichiometry problem like we've done in the past, for example, like going from grams to grams. So let's look and take this example a little bit farther based on this information that we started with. So here's our example again, okay? Here's our balanced equation that we just did. So at STP, that's the key piece of information right here. The temperature's the same, the pressure's the same. What volume of oxygen is required for the complete combustion of 10 liters of methane? Now, like we've seen before in any of these problems, we're only given one number, and that is 10 liters of methane. So, as per usual, the first thing I want to do is convert to moles. So I'm going to put 22.4 liters on the bottom, which is equal to 1 mole of any gas. In this case, it's moles of methane. And then what I'm going to do is I want to convert from moles of methane, and I want oxygen, so I'm going to go to moles of O2, and then I look up at my balanced equation, and I'm going to put a 2 here, and I'm going to put a 1 here. All right, and then I'm going to go my last step. Now that I'm in moles of oxygen, I know that 1 mole of oxygen is equal to 22.4 liters. And again, what I always want to do is double check my units. So liters cancel liters, moles cancel moles, moles of oxygen cancel moles of oxygen. I'm left with liters, which is what I want at the end. And then if I wanted to get real fancy, I'd realize that the bottom unit here is 22.4 and this is 22.4. So those cancel out. So in a perfect world, all this work comes down to 10 times 2, which is 20. So the answer here is 20, 3 significant figures, of course, 20 liters of O2. Now the only time that I can do this is if I'm at STP. There's no weird temperatures, there's no weird pressures that are given, everything is constant. I can just do this volume to volume situation. Let's look at another example. Propane burns in air to produce carbon dioxide and water, another combustion reaction. And oh, look-see, we have a nice balanced chemical equation right here for us to use. What volume of carbon dioxide at 1 atmosphere pressure and 112 degrees Celsius, oh, that's a bummer. That's not at STP, will be produced when 80 grams of propane is burned. Well, the first thing that I want to do here is I need to look at my 80 grams. I have 80 grams of propane, so I want to get this technically to moles of carbon dioxide. And the reason why is I'm at 1 atmosphere, which is great. That's STP. But my temperature is not STP. So that ultimately means I'm going to need PV equals nRT. So let's start with our mantra, convert to moles. So we're going to start with 80 grams of propane. And propane is C2H6. And I'm going to put a multiplication sign and a line. And I will tell you that the gram formula mass of propane is 30 grams of C2H6. And that is equal to 1 mole of propane, C2H6. And then I'm going to go from moles of propane, C2H6, to moles of carbon dioxide, moles of CO2. And then I look up here, and this is a 4. C2H6, there's a 2 right here, so that's 2. And then I'm going to stop right here because I want to stop at moles of CO2. Because ultimately, this is what I'm going to put into my ideal gas law. So if I work this out and everything cancels, I should get about 5.3 moles of CO2. All right, so I'm in the units that I want. Now I go to PV equals nRT. Now the pressure's fine. Pressure's 1 atmosphere. The volume is what I'm looking for. Volume. So I am solving for volume. All right, so I need to put in moles. So I figured out 5.3 moles of carbon dioxide. The gas constant that I'm using here, I've got atmospheres, I've got what it's going to be Kelvin, I've got moles, so this is going to be 0.0821. And then finally I'm going to take 112 degrees Celsius and I'm going to convert that into Kelvin. So that's 385 Kelvin. And when I solve for volume here, it is going to be, let's see, the 3 significant figures. This is going to be, in my calculator, it would come out as 167.5 liters, right? So if I round that to 3 significant figures, it's 168 liters of carbon dioxide. All right. Now remember here, the whole reason of why we did this is because we're not at STP. I can't just go from grams to liters. I just can't go from mass to volume because I have a temperature that's outside the realm of STP. So if you see something like that, then you find the moles of whatever you're looking for, you plug it into PV equals nRT, and then you solve for the variable. The key thing here is that you have to account for this temperature difference, and that's why we did this.